So we're going to look at the haloalkanes or halogenoalkanes group of organic compounds. So as you might guess, these are alkanes, but include the additional excitement of having a halogen in them. Now you would have come across these when you looked at the alkane topic, which is normally studied at the beginning of organic chemistry. And these are made through free radical substitution from alkanes, and you can also make them through electrophilic addition of alkenes with HCl or HBr and so on across the double bond. But how do you name them? Well, the halogen goes at the front, followed by the alkane name. So we have chloro, iodo for iodine, and bromo for bromine. And you just need to remember to put the position of your halogen if required. Obviously, you don't need to for the first two, but once you have a chain length of 3, you do need to put the position in. Physical properties, generally liquids at room temperature, and they don't mix with water. The reason they don't mix with water is because there's hydrogen bonds between water molecules, and halogenoalkanes do not hydrogen bond, and therefore will not mix as with water. So you have two immiscible liquids. They're denser than water normally, so they will sink to the bottom of water. And if we keep the carbon chain length the same, the boiling point increases as we move from chlorine to bromine to iodine being part of the molecule. So let's just consider that statement in a little bit more detail. We're saying for the same carbon chain length, the boiling point will increase as the halogen changes from chlorine to bromine to iodine. But what intermolecular forces are in action between halogenoalkanes? Remember that halogens are electronegative. They are more electronegative than carbon. Electronegativity decreases down the group. We'd expect permanent dipole-dipole forces to be in action between halogenoalkanes, and we know that they're generally stronger than London forces. So we'll look at this in a little bit more detail. Here are the boiling points of chloromethane, bromomethane, and iodomethane. And as you can see, the boiling points do increase as we go down group 7. And we can have a look at the electron filling model. So this shows the electron cloud and gives us an idea about the size of the molecule. And we can also look at the atomic number and the bottom number there for each atom is its electronegativity. So chlorine is 3.16, bromine 2.96, and iodine 2.66. So as we know, London forces depend upon the number of electrons in the molecule, and as the number of electrons increases, the strength of London forces increases. Permanent dipole-dipole intermolecular forces are going to depend on the electronegativity of the atoms in them, the difference between those electronegativity values. And you can see that electronegativity decreases. Difference between chlorine and bromine is 0.2 and bromine and iodine is 0.3. So, as the boiling point increases, which suggests, of course, intermolecular forces are increasing, our number of electrons are increasing, but our electronegativity difference between carbon and the halogen is decreasing. So from that we can draw the conclusion that London forces are more important than permanent dipole-dipole interactions between the haloalkanes. Because if the permanent dipole-dipole forces were predominant, we would expect to see the boiling points decrease as the halogen changed from chlorine to bromine to iodine, but they actually increase as we would expect to see with an increase in number of electrons in the molecule due to London forces increasing. So now we've looked at their physical properties, we can start looking at their chemical reactions. And the first one is we're going to take sodium hydroxide, react it with chloromethane, and that will give us methanol and sodium chloride. So by this method we are producing an alcohol and substituting chlorine for the hydroxy group. So let's have a think about this mechanism. Is it going to be substitution or addition? And what will the attacking species be from NaOH? It's also interesting to think about what do we know about the polarity of the Cl bond as well. And perhaps by adding those ideas together, we can come up with the mechanism name, whether it's nucleophilic or electrophilic, and whether it's addition or substitution. Okay, well, let's see how you got on. So our attacking species is going to be the hydroxide ion, and it's got to be the hydroxide ion because that is what actually is appearing on the molecule in the product. We also know that the carbon-chlorine bond is polar because chlorine is more electronegative than carbon, and therefore the hydroxide ion will attack that delta positive carbon to form a new bond between the oxygen and the carbon, and at the same time the carbon-chlorine bond will break to give me my product of methanol and the chloride ion. So as we've looked at, the chlorine is substituted by OH, so it's a substitution, and I have got a nucleophile attacking that carbon, so the mechanism is nucleophilic substitution. So we can actually study the rate of nucleophilic substitution as we change the halogen from chlorine, bromine to iodine. The main step, the only step in the mechanism is the hydroxide ion attacking the carbon atom and the carbon halogen bond breaking, where X just represents the halogen. So let's have a think about how the rate of that step in the mechanism will be affected as we change the halogen. So there are two things happening here. What property is going to affect the rate at which my hydroxide ion attacks the carbon, and what property will affect the rate of the carbon-halogen bond breaking? Because those two key things must take place for my product to form, and therefore the slower one of those steps will have the determining effect on how fast the reaction occurs. For example, it's no good if my hydroxide ion is attacking my carbon really well, and I've got lots of collisions between hydroxide and carbon. However, that bond is so strong that it doesn't break, and therefore the hydroxide ion cannot form a bond with the carbon. So let's have a look at each of those steps. So the property that's going to affect the rate of that carbon-halogen bond breaking is going to be the bond enthalpy of that bond. Obviously, the stronger the bond, the harder it's going to be for it to break, the more energy it requires. And you can see that as the halogen goes from chlorine to bromine to iodine, the bond actually gets weaker. Carbon to chlorine is 338 kilojoules per mole, but carbon to iodine is only 238 kilojoules per mole. So now let's look at the step circled in green, which is the attack of the hydroxide ion on the delta positive carbon atom. So it's likely to be the electronegativity of the halogen which is going to affect the rate of which the hydroxide ion will attack the delta positive carbon. The more electronegative that halogen is, the higher the delta positive charge on the carbon, and the more likely that negative hydroxide ion will be attracted to it. So let's have a look at those values, and you can see, as we've noted before, that as we go down the group, our electronegativity values decrease. So chlorine is 3.16 and iodine is 2.66. So the bond becomes less polar as we go down the group, and therefore the hydroxide ion is less likely to attack the delta positive carbon. So by using carbon-halogen bond enthalpy data, we would expect the rate to increase as we go down the group 7 as the carbon-halogen bond gets weaker. But if we look at electronegativity values, we'd expect the rate to decrease as we change the halogen down the group. So when we come to test this in the lab, if the reaction rate increases as the carbon-halogen bond enthalpy decreases, then we can conclude that the break-in of the CX bond must be the most significant factor in determining how fast this step and therefore reaction takes place. However, if the reaction rate decreases as the carbon-halogen bond polarity decreases, then the attack of the nucleophile must be the most significant factor in determining how fast the step takes place. So how could we investigate this reaction in the lab? What experiment could we do that would allow us to do this? Well, you'll notice that we're going to be producing chloride, bromide and iodide ions as a product, and therefore we could take how long it takes. We could time how long it takes for precipitate of the silver halide to be produced if we add silver nitrate to the reaction. So that sounds quite a nice little experiment to do. However, as with many things in life, it's not going to be quite that simple for us. Our first problem comes about when we add silver nitrate. Silver ions actually react rather nicely with hydroxide ions. So as soon as we add the silver nitrate, we will see a precipitate straight away of silver hydroxide as the silver and hydroxide ions form silver hydroxide solid. The other issue we have, you may remember from the physical properties of halogenoalkanes, is that they don't actually mix with water. Of course, the sodium hydroxide and silver nitrate are going to be dissolved in water. We then add the halogenoalkane to that, and it will just sink to the bottom of the solution and will not mix with the reactants, and we will not see any reaction take place between the halogen and the hydroxide ions. So two quite major issues. One is that we see a precipitate of silver hydroxide, but that's not what we want. And the reaction that we want to take place won't take place because they don't mix. So can you think of ways around that? We have some hints coming up, but perhaps you could ponder some experimental solutions to get around those two issues. So here are some hints. First one, halogenoalkanes and silver nitrate solution not mixing. So we need to find a solvent which will both hydrogen bond and will mix with water and will also dissolve halogenoalkanes. So think of one which has a carbon chain and also hydrogen bonds. Silver hydroxide being formed immediately. Well, can we do the reaction where we don't have to have hydroxide ions present? This reaction will occur in water. It just takes a long time at room temperature. So hopefully you managed to come up with a few ideas. Here is how it's actually done in the lab. So first thing is, rather than just using water as a solvent, we actually use a mix of ethanol and water because ethanol mixes really well with water, and halogenoalkanes will dissolve in that mixture as well, as will silver nitrate. So we have success there. Our next problem that we have to find a solution to is ensuring that the reaction takes place at a fast enough speed for us to measure the rate of reaction in a reasonable amount of time. So the solution is to use a water bath at 50 degrees C and warm the reaction mixture up. Using a water bath maintains the constant temperature and ensures the reaction is fast enough for us to measure. And we find the rate by timing how long it takes for a precipitate of the silver halide to appear, and then rate is proportional to 1 over the time taken. So when we do this reaction in the lab, we find that the time for precipitate of the silver halide to appear increases in the order of an iodo-halogenoalkane taking the shortest time and a chloro-halogenoalkane taking the longest time and therefore having the slowest rate. So, what conclusion can we draw? Is it the carbon-halogen bond strength which is the most important factor, or is it the electronegativity of the halogen which is most important? Well, since the order is in iodine, bromine to chlorine in terms of the rate decreasing, that would suggest that as the rate decreases, it must be due to the carbon halogen bond becoming stronger, because the carbon chlorine bond is much stronger than the carbon iodine bond. If it was electronegativity that was a predominant factor, chlorine, of course, is the most electronegative atom out of those three, and therefore chlorohalogenoalkane would be the fastest one. And the reason why that is that as the halogen gets larger, the carbon halogen bond will get longer and therefore weaker and breaks more easily. So halogenoalkanes are a really important class of organic chemical. We use them a lot in synthetic routes, so you would have come across them in other modules that you've studied, and they will feature again in the A2 course. So I hope that's been a good little introduction into their properties. If you'd like to download these slides, you can just go to the website, follow the link that will have appeared on the video, and you can download all of these as a PDF from the website directly.